Very good afternoon to all of you, and thank you for joining us in this specific workshop on FDSOI technology for IoT designs. This is probably the first time we are arranging a very specific workshop on a technology topic as a part of the Vision Summit. But the very subject, based on the keynotes that we heard today morning, the importance of IoT and IoT products, I think has sunk in on all of us. So from a relevance point of view, from a contextual opportunity point of view, I think this is absolutely the right time for us to have a workshop which is focused on what works and what will work and what has been researched world over for the suitable technology, process technology required to make the IoT products successful, because IoT products come with very specific characteristics, little different from what we have seen in the rest of the semiconductor ecosystem. Now, it comes with very unique characteristics, so the core building blocks need to meet those characteristics, and that's where the right selection of process technology or technologies become very important. So I have with me one of the world leaders in the fully depleted SOI technology, which we all know is not only appropriate from a scaling point of view, but more appropriate even from a cost per product point of view, or cost per part point of view. So we have Mr. Paul and Thomas from, Thomas, yeah, here he is, from Soitec, and they are headquartered in France, and of course they have design entities in other parts of the world. But I would say today there are others like STMicro, there are others like IBM who are all players in FDSOI, and there is some amount of activity that's happening on FDSOI and even in global foundries. But when it comes to the core technology, and also when it comes to deploying the technology on the product space, and making us understand what it is all about, I think probably Soitec comes right on top of the list. And along with them, of course, we have the technologists from IMEC, Belgium, and also Ajit Manocha, which probably a lot of you know very well, that was the former CEO of Global Foundries, who is coordinating this workshop. So please join me in welcoming them in this workshop, and over to them. Over to you, Paul.
Good afternoon. As Krishna mentioned a bit about my background. Yes, my last job was at CEO of Global Foundries, but prior to that I left India 43 years ago. But my heart never left India. And started my career in Bell Labs. I don't know if you've heard of Bell Labs. Was one of the best research institutes in the world at that time. Bell Labs to Philips to Global Foundries, and now I'm serving on a couple of boards. And what has happened, plus I'm serving on a couple of President's Committee in US. And the word leaked out to India, and I got invited by Indian committees, Indian government a few times to serve on a few committees here. And the question I'm generally asked is, Ajit, how can you help India grow the electronics industry, the semi-industry? And of course, my career and my background has been mostly in fabs. I'm labeled as a fab guy. And one of the questions is, can we build a fab in India? I think everybody wants to know that. I have my views on how to do that. I think the answer is yes, you can do it, but the way we're doing in India is not the right way, but there's a different way to do it. But in addition to fab question, which I'm not going to address in this workshop, I think the question is, how do you really grow the semi-industry in this country? And one approach is that you can just follow the traditional approach of designing the way most companies do the design work, or you manufacture, do the prototypes and go to TSMC or Global Foundries or UMC and do your prototypes. That's a long and very expensive process. If India wants to succeed, the best way to do is to adopt some disruptive approach for disruptive technology to disrupt your industry here. And I have no personal stake in any of these companies that we are talking about here. I've been involved with Soitec and IMEC pretty much from inception. They were both French companies. I was based in Europe when I was the CEO of Philips Semiconductors, which is NXP now, which is going to become Qualcomm. And I have developed an enormous respect for these two companies, among others, especially on Soitec. The technology that I am very much familiar with is the FDSOI. It is my legacy that I started in with the Soitec with Paul Booth, who is my dear friend from Soitec for many, many years. The FDSOI technology gives us so many advantages. Just if you take the core technology, it gives you one generation ahead performance on cost as well as power performance. So, for example, if you have 14 nanometer technology, it costs about $5 to $10 billion to build a fab. With FDSOI, you can make 22 nanometer, which you can take depreciated fab of 28 nanometer at a lot less cost, and yet get the same performance of power and the transistor performance of 14 nanometer at 28 nanometer. Additionally, my association with IMEC is probably the most prestigious research institute in Belgium, has a very strong membership, and you will hear more about IMEC also. They have a fab. Virtually every technology exists in IMEC. Now, imagine for this country, especially for IoT applications, if you are working with Soitec and IMEC, and they will tell you why it is going to benefit, that you have access to fab coming to India for you, access to design technology, access to process technology, and the disruptive piece of the technology which will give you a head start for India. So personally, I met the few of the government officials this morning, and of course several times with Dr. Ajay Kumar and Amitabh Kant and even Ravi Shankar Prasad. I have been approaching the government and preaching that if India wants to be successful, especially the startup companies in India should not just do the traditional way, rather go after disruptive approaches like FDSOI technology, RSOI technology, or RF technology, and work with the entities which are not here just for making money. They're here to promote their vision, promote their mission, and help other countries. So with that, I'd like to give you a brief introduction here. Paul, he's the CEO of Soitec. And you can.
Good afternoon, and thank you, Achit, for the introductions. This is my first time in India, by the way, and I already learned a lot of things, starting this morning with the conference. And one of the things I picked this morning in the presentation was one sentence: don't innovate to compete, but innovate to change the rules of games. And I think this is exactly what we are talking about this afternoon. I mean, it's not innovation just to compete against the big one. It's how are we going to change the rules to get into new markets? There is new paradigms in terms of markets. We talked about IoT, and you will see this afternoon IoT means a lot of different things. But it is about competition at the end, and it's about getting in the market with the right technology, the right design, the right product for the right market. And India is a big market, so I think we are going to share with you a lot of what we do and a lot of what we think. Please don't hesitate to ask questions. At the end, we will have a time for questions, but I think it's the value of this workshop is also to get your feeling about what is missing, get your feeling about what you want to do.
Thomas, you want to introduce yourself?
Good afternoon. My name is Thomas Pilichuk from Soitec. For me also it's the first time in India, and I'm very happy with that. So I am in charge of marketing and business development in Soitec. I've been with Soitec for almost 9-10 years now, and in semiconductor industry for over 25 years. My background is in electrical engineering and physics. And I'll be talking about some of the details of our technology.
Thank you, Thomas. Lode, you want to introduce yourself? And take the seat here so other people standing in the back can take some.
Hello, I'm Lode. I'm responsible for business development in our silicon technology programs. And I will share a few slides as part of the joint presentation we have today. So we'll, as Max said, we're open to collaborate and find technical grounds together where we can work together.
Okay, with that introduction, I want to pass out these sign-up sheets. I'll appreciate if you can put your information about yourself, your coordinates, so that this is not a session that we have today and we're done with it. So there's a follow-up both ways. Either ways, you want to follow up and you have questions, we can help. With that, I think we'll start the presentation. The idea is not to just do the PowerPoint dump here. The idea is to really have interactive discussions after maybe 30, 40 slides. And I really would like that last 30, 45 minutes, a lot of questions. So please ask questions. And now if you don't ask questions, then I will ask you questions. So it's up to you. So please think about questions during the presentation. With that, Paul, I give you the floor.
Maybe one more comment. So what you will see today, it's only just a snapshot. Sorry. So just to add one comment to what Ajit just mentioned, what we are going to present today, share with you for the discussion, is just a small snapshot of what is today FDSOI ecosystem and what value this can provide to the electronics. We will share data coming from various partners, including Global Foundries, Samsung, STMicroelectronics, and few others. But there's much more data available. So this is one of the reasons we'd like you to fill your the presence sheet so that we can then share with you much more the information which is available. So it's you can take pictures here, of course, but we can email to you this material and much more if needed. But please fill this yes.
So I finally can start, okay? But it's a kind of long agenda that we have, but we'll talk about Soitec and IMEC. You need to know what are these companies doing. We'll talk about our technology, Soitec technology, but not as a marketing ways of talking about technology, to tell you, what kind of innovations we bring to the market. The opportunity for India, I think it's very important here, and we will focus the rest of the talk on FDSOI, which is the technology that we really now bring to market for IoT and very low power in terms of applications. And finally, the question and answer. So if we start with Soitec, and Soitec has been founded in 1992, so it's a 25 years company. We have the main building, the main headquarters is in France, in Grenoble in the Alps. But we have also factory in Singapore, and we have sealed manufacturing agreement with a Chinese partner in 200 millimeter out of Shanghai with Simgui. So basically what we do, we basically manufacture wafers here, but these are very special wafers, and I'll talk a little bit about it. But the company is revenue-wise is in the range of $250 million US. We are on the ramp right now. We are a listed company, a little bit less than 1,000 employees, and obviously innovations is clearly one of the focus of our success, and we do have a lot of patents, and R&D is very, very important for us as well as part of the future growth. What we see in terms of capacity, we have about 1 million wafer capacity in 200 millimeter, and we have about 1.5 million wafers capacity in 300 millimeter. Okay, so we have different type of business. We can sell wafer, we can license our technology, and we can also do services. And we get into manufacturing and help some of the manufacturing using our substrates. So what do we do? So we basically buy silicon wafers. We transform these wafers, and we sell these wafers to the foundries or to the IDM, and in order for them to build the chips that goes into the systems. But when we do transform these wafers here, we really bring a new material into the supply chain. It's a material that will impact the performance of the device as well as the power consumptions of the device. Where we do that, I mean, as I said, we have factories in France. We have 200 millimeter factories in France, and the 300 millimeters factories also in France. We are in Singapore. I mentioned that we are also in China with Simgui. What are the markets that we are looking at? When you look at these pictures, basically, I mean, you are thinking, okay, I mean, this is the world we are living in. This is exactly the tools, the applications that we are in every day. Your kids, your family, everybody is touching an iPad or a computer. Everybody is getting into a car. Wearables, computing, and the cloud computing is also some of the market that we are looking at. So why these markets are important to us? Why is it important for Soitec product and Soitec? What can we change by changing the rules of game? What do we try to do? If you look at all these markets here and all these applications, and there is more, there is, in order to succeed, basically, there is basically three things that you need to think of. Every time you think about a new product, you have to think about three things. One of the first things is performance. And clearly, performance is always a challenge as we go into integrated product, IoT, automotive, whatever. We need to reach the performance level. But we need to reach the performance level at the right power consumptions. It's very critical. The only things that you want to do, I mean, you want to use your smartphones or you want to use whatever wearables you need, but you want to use it more than one day, more than 1 week, and tomorrow with IoT, it will be more than a year. So power consumption is very, very important. Reliability, I mean, reliability is also very, very critical in the car and some other applications that we will discuss. And finally, cost. Okay, we can design the best product. We can design the most fancy product. If it doesn't reach the cost level, it will never be adopted in the industry. So we are talking about mass productions. We are talking about very low cost, and that's one of the challenges for our industry. Again, this is clearly the same things, but as we go into our new strategic plan at Soitec, what we start to foresee, I mean, a lot of new applications coming faster than what we were expecting. Okay, basically, visual computing is there, artificial and virtual intelligence is already, I mean, coming to us quicker than what we were expecting. Autonomous drive, the same thing. So as we go forward, we see more and more applications that really can be the right target for the discussions we are going to have this afternoon. So Soitec, basically what we do, we built, as I said, we built engineered wafers. And we start with basically silicon material. And we have a unique technology, a patented technology where we can smart cut very thin layer and move and bond this layer onto a different type of substrate. So basically what we are trying to do, we are building materials here, wafers, with materials that cannot grow on top of each other. Material that cannot be built through depositions or epitaxy or some of the technology that we all know. So the only technology to really get these wafers out with the level of uniformity, the kind of material that you want in order to achieve the performance or achieve the power consumptions that you need, we can design these wafers working with the designer, working with the applications guys. We are working with them to identify what do we need to build in order for you, when you really build your device, you get exactly what I said, the best performance at the lowest power consumptions level and at the right price. So the model we are using at Soitec is not unique, but it's a very powerful model. On the left side here, it's partnership. We are partnering with a lot of R&D center, and IMEC in the room today is one of the key partners for Soitec, because you need to anticipate, you need to understand what is coming. And you will see that, I mean, to bring a technology from 0 to manufacturing, we are talking about 5 to 7, 8 years sometimes. Okay, so you have to anticipate. You need to understand what are the triggers for your industry and for your company to focus on. And also we are partnering with some of the companies where we are licensing our technology, because in order to grow faster, to scale, Soitec is licensing its technology, and we have two. We have Shin-Etsu and Atai in Japan, Sun Edison in the US, and Simgui in China. So, sorry. Yeah, I was going to give the stage to Lode.
Okay, a few words on IMEC and where we come in the picture. So a nice handover slide in collaboration, because actually R&D collaboration is our business model. We don't have products. We are an R&D organization based in Belgium, and we have about 2,500 more people on board, coming from more than 70 nationalities. It's a very international environment, and we have a revenue of, like past year, more than 500 million euro. This is R&D collaboration with companies and institutes. I will show you some more details later. We have a fab, we have an infrastructure, which is quite unique. There is a 10,000 square meter clean room, a number of other labs. The clean room is 200 and 300 millimeter. So we can enable a lot of technology demonstration and prototyping in our fab. This is just in one slide our partners in the semiconductor technology space, where you see more and more, and it was already shown, if you go to new systems, you need to understand technology. So you need to understand the whole value chain, and this makes it necessary that you work together with suppliers for materials, software houses, equipment houses, and then you see the customers coming in, like the IC makers, both logic and memory. You see Intel, Samsung, Global Foundries, TSMC, the memory makers, SanDisk, Toshiba, Micron, Hynix, but also design companies. So many, the big names are there, like Qualcomm and ARM, and many others that are not listed in this overview. But this is a complete ecosystem on where we try to combine technology enablement and new systems. And so given the IoT, so what's the technology focus in IMEC? So you have a number of, I would call it platforms, but it's very broad scale, because if you go the range, it goes from very advanced, what we call core CMOS, advanced scaling. You go in FinFETs and you squeeze Moore's law to the last nanometer, so to say, whatever is possible there with advanced lithography. At the same time, we have platforms in heterogeneous integration and in flexible electronics. Heterogeneous serving MEMS, serving sensors, where it's often bilateral work together with companies. And the flexible is more on foil. It goes into larger scale, can be printed, and also there you can make circuits and displays. Now, what are the application areas? There are three big drivers. One is what we call the intuitive Internet of Things, everything related to, oops, some pictures are disappearing, but doesn't matter. The Internet of Things, the wireless, both in high bandwidth, so for 5G, or in the house on shorter range, 60 gigahertz, radar technologies for the car, 79 gigahertz or more. All this requires various different design blocks. This other part is health. Health is a very big growing opportunity. It's a long shot in terms of investment, but rewarding. There are applications where the idea is really to make devices, not gadgets, but devices that become part of the doctor's office, that measure, sense, biomedical, bioparameters, and silicon can be used as a cost-effective platform to make large-scale devices. And the third one is the Internet of Power. Power is very important, so energy devices, power devices like gallium nitride, photovoltaics, also organic photovoltaics in building integration and so on. That's like the whole of IMEC. This one just to show the roadmap. We're entering, it's very important to know that the day that one technology roadmap is serving all applications is behind us. So what you need is each application will require different platform. Whether you look at, even in the IoT is everywhere. It's in the server, it's in the cloud, where you will have advanced performance devices, and you have the wearables, the mobile devices, where you will have different platforms. And that's also where the technology of this afternoon comes in, where you have a trade-off focusing on low power, enabling combination of technologies you combine with RF, etc. So you look at, for instance, a typical IoT component, an IoT node, it's much more just than a logic chip or a processor. It will have enablement for RF, for wireless. It will have an MCU, but it will also, or it can have sensors. It can have possibly a display, an embedded memory. So in that sense, there is a broader range of technologies you need to enable. And this is also where FDSOI comes in as a very good and excellent platform for a set of these kind of applications. That said, we can go further into detail this afternoon. This was just to illustrate what we do. The collaboration possibilities in this technology can both be on the design part, on the library part, on the technology itself. We can discuss, and there are a lot of opportunities. Thank you.
Thank you, Lode. So with that, we'll go now more into details of Soitec technologies and products. And you know, the main Soitec technology, it's called SmartCut, which, as Paul mentioned, it allows to take very thin slice of silicon and then bond it on something else. If you make SOI, which is called silicon on insulator, you bond it on oxide, but you can do it with any other material, which can be it can be sapphire, it can be glass, it can be many other things, depending what type of performance you are looking for. And we'll get into it a little bit later. But there are the three main technologies in Soitec: the SmartCut for SOI, smart stacking, so bonding different materials together, and then epitaxy, so bringing 3-5 materials for various reasons to improve mobility or to bring new features into the substrate, which at the end finish up as a part of the transistor. So it becoming heart of what you're looking for as a designer, as a chip designer in getting performance. As Paul mentioned earlier, here are the key markets, we are serving today with SOI, silicon on insulator. Radio frequency, we'll talk about this. It's the first big success of SOI. Fully depleted SOI, this is the main topic for discussion this afternoon, but also some other markets like power markets and some new markets like, for example, going to satellites or some of the AR, VR type of applications. And here you see just a snapshot of the customers of SOI. So today SOI, it's not a niche technology anymore. It's not a niche application. Many of you heard about SOI probably in the school. This been on the market for some very small specific applications for 25 years, because the value of SOI by, from physics standpoint is low leakage, it's lower power consumption, and higher reliability. So, over 2 decades ago, it's been applied in some, satellite applications, in some military applications, and started to go slowly through IBM to servers, to some gaming applications, but still very close type of ecosystem and very few applications. Now we made a breakthrough, and now we'll show you the story where with the two specific products, RF-SOI for radio frequency, and now with FDSOI, fully depleted SOI, we are reaching very big and open markets, which will be also attractive to you. So here you see the range of the products and type of SOI products which are in growing markets today. FDSOI, again, we'll talk more about that in a while. Radio frequency, and then power SOI. So this is a type of application you find today in automotive industry for again high reliability, for high voltage type of switching applications, transceivers. So there's more and more of this type of devices on the market. Half of the cars manufactured every year have this type of substrate in the chips because of this high voltage or mid-high voltage performance value. Silicon photonics, you heard probably in the main session earlier this morning that silicon photonics in data centers is becoming a big trend, where the very high data computing and data transfer in data centers will require very different type of connectivity. And SOI allows to build interconnection between servers, racks, and even more between chips and in much better way, with allowing much faster communication, going to 100 gigabytes and higher. And then finally, also SOI for image sensors and other sensors. So this is for visible light sensors, can be infrared sensors, and many other types of MEMS sensors where SOI can be used. So this is a huge range of different applications and different products. They have the starting point, which all of them are SOI, but all of them are very different. They're using very different silicon on insulator, but when you get into details, they're very different crystal, very different type of material used. You see here there's additional layer which is within this stack. We are using higher resistivity or specific resistivity material. All that is to provide at the end specific performance to the device which is built on this stack. So what Paul mentioned earlier, we are not selling just starting material. We are providing solution which already includes some of the performance of your device. That's why it's so critical to fit this material, this engineered, how we call it, engineered substrate, with what designers need. And that's why when on the previous slide here, you see here foundries and IDMs, so people who make chips. But you see also here names of people who are fabless or end customers. But at the end, these guys are interested to understand what is here in these substrates, because at the end, their device will depend on that. So we are working a lot with these people who are not manufacturing chips, but designing chips. And this is something also which I think is key point for you, is that if you design chips, you may want to know, what value at transistor level materials can provide. One word about all the journey to get to this high volume mass applications, and I think Paul and Lode mentioned that it's a long journey, and it starts with R&D, and it starts with partners like IMEC, like UCL, like Leti, like IBM. So this is the beginning of putting this technology together, and then it's going through all the value chain to get the product on the market. But it can be 7 to 10 years between the big conception to the product being on the market. But again, IMEC is one of the key partners who over several decades now has been developing with Soitec and many partners. I'm always impressed with the slide from Lode showing all the partners from IMEC has, because the slide is getting denser and denser every year. But this type of partners here in India can bring a lot of value to help to develop customized solutions. There's different way to look into what type of value you can bring within semiconductors. There is this trend which has been going on over the last 4 decades called Moore's law, where with the scaling, you're improving performance every couple of years, and we are getting to some limits of that, and we'll talk about it later. And then there is the other way is to bring here is a slide from Global Foundries, bring it from differentiating silicon, or we call it engineered materials. And RFSOI or MEMS or FDSOI are part of the solutions which bring different value to the device in other ways than just scaling. And then there is system level integration, and there are different ways, and here silicon photonics is one of the solutions. But today we'll focus on these 2 elements, on RFSOI and FDSOI. And RFSOI, it's a big success story. Would like to share with you just few elements of that. Don't know how much radio frequency chips. Here you see front-end module from any mobile device, from smartphone, with PAs, power amplifier switches, and all the complexity going from 3G to 4G to LTE and so on. And before till 2G and beginning of 3G, most of this technology or this design was based on gallium arsenide. And today, almost everything got replaced by SOI. Why? For performance, for lower power consumption, for integration, and for shrinkage. So there is multiple differentiation value which SOI brought into RF market, which today allowed industry to move from 3G to 4G to LTE Advanced, and beginning of 5G roadmap is also based on this type of materials. Different generations of this material, but it's all RFSOI. And it's amazing because over the last 4 or 5 years, it went from nothing to really full adoption. And today there is no single smartphone in the world without RFSOI in it, and there is no single specialty foundry. And you have a list here. There's more than 10 of them, and all the leaders in RF design. And you see all the big names here who are not using RFSOI. So this has been very big success, and you see that from one generation to another, the content of SOI in smartphone is growing with the complexity of RF, with higher specs of communication. It's this is type of the value SOI can bring, and again, it starts with connecting with designers, people who think about integration, the chip performance in RF business, like here, and then they bring this ideas how to integrate new functionalities and new performance into SOI, which can boost this performance for them. So this was first example to show that SOI it's now in the market. It's a global market, and with really became a standard in the industry. And we'll talk next about how FDSOI, fully depleted SOI, is becoming a standard for low power applications on digital side.
Thank you, Thomas. So you can see that there is many ways for India to also think about how to grow into this business. There is a lot of differentiated technology, but there is one thing that you have to think about is what do you want to avoid in order to make probably the best choice. So what you need to avoid to reinvent the wheel, and you need to decide to go with and to pick the right partners and also the right technology in order to go faster and to become mainstream. That's very important. So one of the things that we wanted to focus here for India is we believe at Soitec, we believe that the future of semiconductor is linked to innovative materials and design process integration, and that you must benefit from partnerships around the world, and you must benefit from the newest technology. Again, it's not innovations to compete, just to compete. It's really innovations to change the rules of game. And so on that, I think that what we bring ourselves, we bring a new way in terms of looking at the performance of the device and the market. And we also believe that we have built around us a very strong ecosystem from design, partnership with IMEC, and also up to manufacturing. We want to go focus now on FDSOI, and we'll come on the next slide on FDSOI, because what is the most important things in front of us? It's mobility. And how are we going to address mobility? What kind of technology, R&D partners, designs partners, what do we want to achieve here in order to go fast and to go faster than competitions? We believe that we have, through the FDSOI market, and I will show you more examples, that we have now the entire ecosystem to come and help. Help with our partners, help with our materials, but help all across the supply chain in order for some of the startup here, companies who are interested in getting into full speed, we can really accelerate their innovation process. And again, it's all go with partners. I mean, you can be big or you can be small. The success in this industry is through partnership. Okay, it's too complex to get the full package and run it alone. I mean, you will be late. It will be too expensive. You will make the wrong decisions. So partnering is very, very important. So I think this is an interesting topic because everybody knows about Moore's law, right? You understand what Moore's law means, the scaling of the device on a 2-year basis. And Moore's law is going to continue. Moore's law is not going to stop. And this is the schematic of Moore's law going from 90 nanometer, then down to 28 nanometer, 16, 14 FinFET, 10 FinFET, 7 FinFET. And now the next generation is already under R&D. I mean, we are talking about 5 nanometer and 3 nanometer. So is this technology going to continue and to grow? The answer is yes. And we need it. It's going to be for high computing, very high computing capabilities. When you have a device, when you build a device that is going to run full speed all the time, where computing is very important, you don't have the choice. You go this route. And this is the best route. But we will have some interesting discussions moving forward, because this route is very, very expensive. Starting 28 nanometer, the world, our industry has been on shock. Over the last 5 years, the industry has been trying to really work on this technology to make it affordable, because it is a very expensive technology. And remember what I said. I said you need 3 things. You need performance, you need power consumptions, and you need cost to be successful. So 4 or 5 years ago, Intel came up with this strategy to bring this technology, because the world was stuck. 4 or 5 years ago, we were doing CMOS like 30 years ago, planar CMOS on bulk technology. But at 20 nanometer, this device really do not perform with the right level of performance and the right power consumptions. If you want to get the performance at 20 nanometer, you cannot get the power consumptions that you need. If you want to get the power consumptions that you need, you cannot get the right performance. So basically, the industry knew that around this 20 nanometer, we needed to think about a new approach, a new way to design a transistor. So Intel, at that time, 5 years ago, came up with, we need to build a transistor on a wall, okay? Because there is so few electrons moving through the gate that you cannot have one missing at the end. So we need to really build a design where we totally understand what's going on, and we put these electrons in a gate that they cannot escape. That's one way to think about it. So the complexity for the industry was to really change everything. When you think about modeling, it's a new modeling. When you think about IP, it's a new IP. When you think about manufacturing, it's a new manufacturing. Okay, so that's a big jump into something that was needed, that is needed, because we need to develop a transistor that is capable to, again, deliver the performance and the power consumptions at the right cost. 5 years ago, 4 or 5 years ago, we came in, with Soitec, we came in with a different solutions. We came in with a different solution, and we said, okay, instead of having the transistor on a vertical wall, we can stay planar, and Soitec will bring the innovations where this ultra-thin layer of silicon will be standing on an ultra-thin layer of oxide, silicon oxide, and we will have the same physics. Okay, we can get the same physics, but we can stay planar. We can reuse the same IP, we can reuse the same modeling, we can reuse the same manufacturing. To tell you the story, because it's always good to think about history. 10 years ago, Intel came to Soitec and asked for this. 10 years ago, Soitec was not able to produce this material. And you know that the big guys like Intel, they have their long process of innovations that at one point they have to make decisions. So because they didn't have any alternative at that time, they decided to go this route, which is fair. That was the right thing to do. Okay, but as we were French and trying to think, why are they asking us to do into these directions? Why is it important for Intel? Then we started to continue to work on this and came up with the right capability to produce this wafer. So the complexity is that when you come with a new product to address a market that is already pushed by the technology leader, you get some resistance. So 4 or 5 years ago, we were going around the world and said, we have an alternative, right? This alternative is to stay planar. Cheaper for you, easier to design, easier in terms of getting the performance right at the right cost. But the industry really, decided that one technology could really do the job for all applications. So that's the history. But again, I would just want to demonstrate the physics. Okay, so what we are talking about here, we are able now to bring a very thin layer of oxide. This is at the wafer level. So we have a very thin layer of oxide. We are talking about 12 nanometer. And we can go down below 12 nanometer on a very thin layer of silicon on top of silicon oxide. And this is how we built these fully depleted devices. The innovations that we bring is clearly, when you look at the top silicon layer, if you basically fly from Paris to Bangalore, then it's plus or minus 1.3 centimeter on the flight, and basically it represents plus or minus 5 angstrom across the wafers. So that was the innovations that Intel 10 years ago was asking Soitec to deliver. Kind of, can you, across a 300 millimeter wafer, can you get this uniformity on an ultra-thin silicon layer to achieve that the level of performance? So the problem is, when you look at the top silicon layer, if you basically fly from Paris to Bangalore, then it's plus or minus 1.3 centimeter on the flight, and basically it represents plus or minus 5 angstrom across the wafers. So that was the innovations that Intel 10 years ago was asking Soitec to deliver. Kind of, can you, across a 300 millimeter wafer, can you get this uniformity on an ultra-thin silicon layer to achieve that the level of performance? So that this route that the industry has been using has shown a little bit of problems here. And the problem is very simple. This technology has delivered in performance, yes, has delivered in power consumptions, we can say yes, but did not deliver on cost. The cost per gate, and you will see more example, from here to here is going up. The cost of design is going up dramatically. The cost of modeling is going up. And 4 or 5 years ago, as the industry was moving into this, we were all hoping that a lot of new systems, new tools like EUV and some other systems in the factory could really come and bring the cost at an acceptable level. It has not been the case. And what the industry has agreed now, the industry has agreed that this technology is going to move very quickly to 10 nanometer and 7 nanometer, because at 7 nanometer, this is the right spot for performance, for power consumptions, and for cost. Okay? So the industry is now, the TSMC, the Intel, the Global Foundry, Samsung, they are all moving this technology very quickly to the 7 nanometer, and it will be a 5 nanometer in the next 2 years. And this technology is going to support basically all the very dense chips, the chips that are really supporting high-performing market, high-density type of applications. When your device has to run full speed, like a microprocessor, graphic chips, basically, I mean, there is no other way. You have to go there, okay? And you have to pay the price, and but the infrastructure is there, and this is the only way to go. Now, the big names, like over the last 2 years, the big names like Samsung and Global Foundries and ST Micro, they understand about this roadmap because they built devices on this roadmap. But they understood 2 years ago that one technology will not really match all the applications. And specifically for IoT, specifically for mobile application, this is a very expensive technology that will not be able to really fit into the mobile world. By mobile, I mean wearables, I mean health, I mean some of the automotive applications. And basically, I mean, and that was the tipping point for us as well, because it has been recognized by Samsung, by Global Foundry, by ST Micro, that the world, the industry, needed a new roadmap, an alternative roadmap. Okay, it's not one against the other. It is more what chip you want to build and for what applications. And then you have the choice. And so we have seen Renesas starting at 65 nanometer, FDSOI for very, very ultra low power applications. And basically also we have now 28 nanometer at Samsung and ST Micro, 22 nanometer is ramping, qualifications is going on at Global Foundries. And they just announced a 12 nanometer also for Global Foundry. And these platforms, these foundry platforms really accelerated the adoptions process, and we'll come back on this. A couple of examples on why, on what to support what I said. If you look at the cost per gate by process generations here, you see that 28 nanometer bulk is the bottom, and starting here at 20 nanometer, we start to be on a plateau, and 16, 14 nanometer, we go up. So the price, the price per gate, the cost per gate is going up, which is the first time in the history of our industry. And so we needed to find a way to overcome this. If you look at the design, same story. Around 28 nanometer, moving to the next step, the design cost is dramatically increasing. So basically, I mean, if I want to make a short story, if you sell a smartphone at $1,000 per piece, your application processor that is in this smartphone can probably afford this because you have a huge market and the price of the tool itself is very high, so you can really have a business that works. If you sell this smartphone at $500 US, it doesn't work. Okay, if you think about Apple, because this is an Apple phone, if you think about Apple in these phones, they use probably a 16 nanometer FinFET, okay, technology. If you look at the Apple Watch, it's the application processor inside the watch, it's a 40 nanometer application processor. And they are getting with their watch into these low power problems, battery situations, these kind of things. So again, even for one brand, you have to decide and to pick the right technology in order to make a profit at the end. So you need to address the market with technology, but also with cost. And it's very important. A few other examples in terms of, and these examples are, the source are, this one is from Global Foundry. I mean, this is not Soitec data because we cannot really show that. But again, the Global Foundry here is showing that the 22 nanometer technology on FDSOI in terms of performance is equivalent to a 1614 FinFET if you can use what they call a design trick with our technology, which is the back bias, and Thomas will talk about it. Same at 12 nanometer, they can compete with in terms of performance, and overall in terms of mask set, you can see that they use basically 60% of the level of mask set. So basically, you can reduce the cost of manufacturing. You can simplify your manufacturing as well. Same in terms of overall cost of development. The cost of development is really jumping after 22 nanometer, and we can really reduce the price and the cost, of developing with FDSOI technology. Another example showing by ST, and this is more on the manufacturing. So basically what ST was demonstrating here, ST Micro, they were demonstrating that they can reuse 90% of the manufacturing that is being used in bulk silicon, standard technology, can be reused for FDSOI. And basically, it is, if you think about the process simplification, including the price of the substrate, because our substrate is costing more, they can really come to a much lower wafer price at the end of their processing because they can simplify the technology. And that's coming from another company, IBS, who is showing that basically the wafer cost on a 12 nanometer FDSOI is basically cheaper than a 1614 nanometer FinFET. So everything I said is to tell you, is to make you understand that you have the choice. And what the industry is now mature enough to provide the choice to India. And you have to decide on what kind of product you want to focus, what kind of market you want to focus. And from there, you can really go down and decide on what technology you want to bring.